All right, guys, so we are going to be talking about logarithmic differentiation. All right, so it's a technique that makes our life a little bit easier. So let's look at an example, and the instructions would be to differentiate, find y prime, something like that. And then our function in this case would be crazy. So let's write out a crazy function. Okay, so we're seeing chain rules that we'd have to use. We'd have to use quotient rules. We'd have to use product rules. We'd have to use our trigonometric, our exponential derivatives, the whole shebang, right? So one way to make our life easier is we can use logarithms to break up the right-hand side, okay? And then that process is called logarithmic differentiation. So what we're going to do, our strategy for this concept is we're going to take the logarithm, or the natural log rather, because we know taking the derivative of the natural logarithm is so much easier. We're going to take the natural log of both sides. Okay, which is an allowed operation because a logarithmic function is 1-to-1. Okay, so we're going to do something like that. And then now that we've created a logarithm on the right, and let me write out the whole thing. We can start to separate this really complicated function. We can separate it, because it's an argument now, we can separate it using all of our logarithm rules. All right, so let's practice that. So first thing we could do, we would have to do our quotient rule first. So let's take our numerator, take the logarithm of that. Whoops. Let's try writing that again. And subtract it from the natural log of the denominator. Okay, so then this term is set. That term's good to go. This term, this argument has a product, right? We have two factors. So I'm going to go again. And I'm going to separate out that product. Remember how we do that? With addition. Okay, lovely. Oops. All right, and then we have one more rule we can use. We have a couple exponents. We have an exponent here, right, negative x. What's the exponent here? It's 2, because cosine squared x is really cosine x squared. So let's move those exponents out. Here, I'll write this here as well. Remember, it's the natural log. All this is equal to the natural log of y. That's going to be important in just a second. Oops. Let me do what I actually said I was going to do. Negative x, bringing the exponent down front. Alrighty. Okay then, so now that we have this, and if you wanted to, we can even rewrite that, because what's the natural log of e? It's just 1, right? So this whole thing is just going to be negative x. Okay, so this isn't y. This function right here is not y. It's the natural log of y. So what we're going to do now, because our goal is to differentiate. Here, let's go back up. It's to find y prime, okay? And right now we have a function that's the natural log of y. So what we're going to do, and let me write this out, is we're going to do our implicit differentiation. We're going to take d dx of both sides and solve for y prime. And that's our implicit differentiation. All right. I'll just write implicit diff. Okay, so that's the process. Let me tell you what we're doing again. To do our logarithmic differentiation, you take the natural logarithm of both sides. I'll put a star right here so we see it. Separate it out. And then you take the derivative with respect to x of both sides and solve for y prime. And there you go. Okay, so that's what we're going to do. We're going to take the derivative of both sides. I'll use orange. And then after, you distribute and everything, it's like taking the derivative of each term. Remember, natural log of e is 1, so it's just going to be negative x. I'll move the constants out front because we're allowed to do that. Okay, so let's hop to it. And remember, when we see the y is a function of x, so we have to treat that as a chain rule. So we'll start on the right. So the derivative of the natural log of u is 1 over u, right? 1 over y in this case, times the derivative of y with respect to x. I'll just write y prime. You can write dy dx. Okay. Derivative negative x with respect to x, negative 1 plus 2 times. All right, so outside function is natural log. So it's going to be 1 over u, so 1 over the argument, times the derivative of the argument. Derivative of cosine is negative sine. It looks like it's going to be a negative tangent. And then almost done. Natural log, again, it's 1 over the argument times the derivative of the argument. That's your chain rule. All right. So there you go. So that's the first step. And then let's see, we can clean this up a little bit. And let's do that. Then we're almost done. So negative 1, let's see, we have the plus 2, but then sine over cosine is tangent. And then let's move that negative to the front. So minus 2 tangent of x. And over yonder, not too much simplifying. We'll do minus 2x plus 1 divided by that denominator. Okay, so good. So when we do our implicit differentiation, we figure out where that y prime is, and if it has a y prime, it stays on the left. This time we're going to multiply out by y to clear the coefficient. Okay, so if we multiply both sides by y, that will get canceled. And we have y prime is equal to y times that big thing. And then if we were asked to find the derivative of y, right, and the original function, all the way up here, was given in terms of x only, that's what we have to return. It's only polite. So your last step is to make that original substitution, that y is equal to this big old function. So let's write that, and then we'll call it a day. Okay, and then that's the derivative. So then y prime is equal to y, which was originally defined to be this. times this. All right, and then that is your solution. Okay, so logarithmic differentiation. Let's try one on your own. So again, review the steps. First, you take the natural log of both sides. You clean it up using your logarithm rules, okay? Remember that it's going to be equal to the natural log of y. You do your implicit differentiation. So take the derivative of both sides and then solve for y prime. And then that's how you get your answer. So you guys are going to do that process for this function. Let's find dy dx using logarithmic differentiation. I'll shorthand it. If our function is equal to the following: square root of x e to the x squared minus x times x plus 1 to the 2/3. All right, so go ahead and push pause and then come on back and we'll see how you guys did. Okay, so let's see how you guys found the derivative. So the instructions were use logarithmic differentiation. Okay, so that's telling you to use this technique we just talked about. All right, so that means we're going to take the natural log of both sides first, and then we're going to separate everything out using our logarithm rules. And I'm looking at this argument on the right, and there's no quotient, so I'm definitely not going to use quotients. The whole argument isn't being raised to 1 power. Actually, all the factors are being raised to different powers. So let's separate out the factors first. So we're going to use our addition rule. Don't forget the natural log of y. That's a common mistake, is to leave it at the gas station. All right, and then now we can clean all of this up and bring those exponents to the front. Remember, root x is like x to the 1/2. So I'm going to move the 1/2 in front. Okay, this is a property. This natural logarithm is an exponent, right? And it's saying e to what power is e to the x squared minus x. Well, the exponent is x squared minus x. That's one of those, again, composition of inverse functions is like the identity function. So we're just going to get x squared minus x thrown right back at us. And then the last term, we're going to bring the exponent to the outside. And now at this point, there's nothing else to do. So we're ready to do our implicit differentiation. So again, that entails taking the derivative with respect to x of both sides. So let's see how you guys did with that. So y is a function of x. So we have to use the chain rule. That's how implicit differentiation works. So 1 over y is the derivative of the natural logarithm times, again, you can write y prime dy dx. It doesn't matter. Okay, and now derivative of the first term, 1/2, and you can worry about the constant after. Natural log of x is 1 over x. That's lovely. No chain rule required. The good old days. Derivative of just x squared minus x. Well, that's going to be 2x minus 1. All right, and then finally, chain rule again. This is going to be 1 over the argument. And then the derivative of x plus 1 is just 1. So I'm not going to do anything else with that. Okay, lovely. Let's clean it up. 1 over 2x plus 2x minus 1. And then here, let's see, 2 will stay on the top, and then 3 times parentheses x plus 1. That's good. Okay. So remember, with implicit differentiation, you have to solve for y prime, because that's what the question asked. It said find dy dx, find y prime. So let's multiply both sides by y. And again, if we start off with a function of y that's just in terms of x, and we find the derivative and there's a y stuck in there, that's just rude. So let's make sure we give them back what they started with. And they started with a function in x. So we're going to make the substitution. We're going to say that y is equal to that original function. I guess I didn't need parentheses since it's just a giant product, but it's okay. Wonder if I can erase. But we definitely need parentheses around this part because it's not a product. It's a sum and a difference, or it's a sum. Okay. And there you go. So a ginormous derivative, right? And we got to use all these fun techniques. All right. So what else can we do with logarithmic differentiation? Well, we've had some situations using exponents, and I kind of want to just remind ourselves of all of our exponential situations. We have the case where we have our base has a variable in it. All right, so our base has a variable in it, but our exponent is just a constant. Okay, we have another case where our base is a constant, and now our exponent has the variable in it. So maybe something like this, okay? And we have different techniques. Over yonder with the y prime, you know, we have our exponent rule. So if this was the case, we bring down the exponent, you know, subtract 1 for the new exponent, and then we take the derivative of the inside function, right, using our chain rule. All right, so we have that situation. It's our, a simplified rule is when y is equal to like x to the nth, y prime is n times x to the n minus 1. Okay, so that's one case with the exponential functions we have. And now f prime of x with a constant in the base and a variable in the exponent. Again, we can use our chain rule. We'd have to do 5 to the 2x squared times the natural log of 5, and then times the derivative of the inside function. Okay, so that rule, let's make it more basic. If we have base b to the x, so constant raised to a variable, f prime of x is equal to b to the x times the natural log of b. Okay, so that's kind of our brief little review, okay? And, you know, we have our very simple examples, and we saw that we could get much more complicated, okay, and using the chain rule and such and things like that. The situation we're headed into now is we're going to have a function. So again, it was either, you know, constant raised to a variable or a variable raised to a constant. Constant raised to a constant, awesome, because that's just a constant, right? Like 3 to the 5th. But our last case that we have to figure out is when we have a variable and we're going to raise it to a variable. And we don't have a technique for that yet. So for instance, we have a function and it's raised to another function of x. Okay? And in this case, we can't use our power rule all right? And we can't use our exponential function rule. So how are we going to solve this? We have to use logarithmic differentiation. So before logarithmic differentiation, it was kind of optional. It just made our life easier. But in this situation, variable raised to a variable, we must use logarithmic differentiation. There's no other way to find the derivative. All right, so let's see what it looks like. Let's consider this example. Y equals variable x raised to the cosine of x. All right, so again, there's a variable in the base and a variable in the exponent. And the instructions would, differentiate, find y prime, find dy dx, something like that. Okay, so we have to notice that first, that there's a variable in the base and a variable in the exponent. We have to remember our strategy. That's telling us we have to use logarithmic differentiation. Okay, so what's that process? Well, first we're going to take the natural log of both sides. And then that way we can simplify the right using our logarithm rules. So bringing that exponent down in front. All right, and then once everything is cleaned up and separated as much as we can, then we're going to take the derivative with respect to x of both sides. Okay, and remember y is a function of x. So natural log of y is 1 over y, the derivative of that rather, times dy dx, or y prime. Okay, and then we're going to take the derivative of this. What rule do we have to use? Our product rule, because we're looking at a product. Okay, so I'll start with the second function. So cosine of x times the derivative of the second function plus the natural log of x times the derivative of the first function. Okay, so let's clean it up. Ooh. You know what? Let me rewrite that. I'm going to put that negative sign of x in front of the natural logarithm. I think that just looks better, right? It looks a little cleaner. Okay, good. So now with implicit differentiation, we're going to solve for dy dx. So what do we have to do? Let's multiply both sides by y. I'll switch colors, just kind of break up all that blue. And make sure you multiply the entire right-hand side by y. So you're going to need parentheses. Okay, and again, it's rude if we start off with a function of y or a function in terms of x and we give back y. Okay, so y is going to have to be substituted for that original function, which was x cosine of x, and then parentheses, and the rest of our function. Okay. And then that's our solution. That's our answer. So that's the derivative of x raised to the cosine of x. Okay, so a little bit crazy. So let's have you guys practice. The instructions again would be find the derivative. And now if y is equal to, we'll do that original function we suggested, square root of x times tangent of x. So go ahead and push pause, and then come back, we'll go over your solution. All right. So variable raised to a variable. That means we have to take the natural log of both sides and do logarithmic differentiation. Okay, and the reason why we do that is when we take the log of both sides, now we can bring that exponent with the variable down so we can work with it, right? Okay, and then you can even take it a step further because the square root of x is really x to the 1/2. So I'm going to move that exponent to the front, but it's a product, so I can move it all the way to the front. We can interchange factors. All right, so now it's time to do our implicit differentiation. We're going to come in and we're going to take the derivative of both sides with respect to x. Let's see what we get. Okay, we're going to have to use the product rule. And again, you can just move that constant out to the front and then worry about it after. So we're going to take the derivative of tan x natural log of x, and we're going to use the product rule. So we'll do the first function times the derivative of the natural logarithm plus the natural logarithm times the derivative of the tangent. Okay, and we'll clean that up in a bit, but we have this y right here. So let's multiply both sides by y to clear it, and then we have an expression just in y prime. All right, so y times 1/2 is y over 2. I'll clean this up while we're working. I like to put functions in front of logarithms just for clarity. Then we know exactly what the argument is. Otherwise, we might mistake that secant squared might be part of the argument. That's why I move functions in front of the natural logarithm or the logarithm. All right, we're almost done. We've talked about it before. It's weird, or it's rude to give them y's when they handed us x's. So this is our final step, is to make that substitution. And now your derivative is equal to root x raised to the tangent of x over 2. And then times the rest of our function. Okay. So there you go. So let's go ahead and pause. And when we come back, we're going to be focused on some proofs using our logarithmic differentiation.